subject that we will talk in this lecture is not quite essential for circuit theory, in the sense that it's sort of independent of what we have seen so far, and also of what we will have seen, okay, at the end of the semester. So it's not essential in that sense, but it's too beautiful to leave out, so therefore we say a few words on it, okay. So we'll talk about symmetric circuits now, and by which we mean the following. If given a circuit that we want to solve, if it possesses some sort of symmetry, then computations sometimes may be much easier, okay. So if you exploit that symmetry, and in this lecture we will see a couple of examples where symmetry is exploited to reach the answer through a shortcut. Okay. So, for instance, consider the following example. Okay. Let this be our one port that contains only LTI resistors. Okay. And for this one port, there is an input resistance, and that's what we're trying to figure out. Now, if those resistances are arbitrary, then what we do is we can use delta to Y transformation perhaps, or we can connect a test source to it and figure out and solve that circuit, and by taking ratio of voltage to current at the port terminals, we can find input resistance. Okay? But suppose that the resistances are such that this is R1, this is also R1, and this is R2, this is also R2. And this bridge resistance is something that we call R3. Okay? Now, for this special configuration, we immediately recognize a certain symmetry. That is, if you consider this line as axis of symmetry, the distribution of resistances are symmetric with respect to that horizontal line. Now the question is, how can we make use of that symmetry, or what are the implications of that symmetry? Okay. Now, for this, let's connect a test source across the terminals. Okay. R1, R2, R3, R1, R2. Okay, let this be IS, and this source will generate all sorts of currents and voltages throughout the branches of this circuit. Now, what we ask is the following question: what's this current flowing over R3? Okay, question: what's I? Okay, and the answer is, which may not be obvious at first, because of symmetry, that current must be zero. Okay, now let's see why. Here is one way to think. Now, by linearity, okay, because that's a linear time invariant circuit, any output, for instance this current, is a linear function of the input, which is IS. So by linearity, the output equals some constant times the input, alpha times IS. And that alpha, that constant, depends on the circuit parameters. And now, because of symmetry, now we're going to see that alpha must be zero. Okay. For some constant. Okay, now now rotate the circuit about the axis of symmetry. Okay. Now, what we mean by that is the following. This is the axis of symmetry. Okay, so what I do is, I suppose that I take this circuit is running and generates some current. Suppose that I take this circuit out of the board, rotate it 180 degrees around axis of symmetry and put it back on the board. Clearly, that operation will not change anything. It's still the same circuit. Okay, I'm just redrawing in a sense. So let's do that and see what happens. Okay. Once again, what I'm doing is I'm taking the circuit out, rotating it 180 degrees, and put it back on the board. And if I do that, this is what happens. Now again we have the same shape, okay, but after rotation this arrow now pointing down. Okay. And then let's also do the labeling. Okay. So that IS is now rotated. Yes. Okay. Here we have R1. Here we have R1. This R1 is this R1. This R1 is that R1 and so on. And then we have R3. Okay. Now clearly these reverse labelings has no significance for the actual currents and voltages. Therefore, let's redraw it in a more legible way. Okay. So this is R1, this is R1, R2, R2, R3. Okay. Now the current still is in the same direction because rotating around the axis of symmetry doesn't change the direction of the current. Okay, so we still have the same current in the same direction. But that rotation changes the direction of this current, however. So now it's pointing down. So we have pointing down IS, which is equivalent to pointing up minus IS. Okay. And now compare this circuit and this circuit. Okay. Now in this circuit we have IS from the input and that generates some current I. Now for the same circuit we now apply the negative of the same input. Okay. Minus IS is the input, but still it doesn't generate I, but it generates minus I, which it should by linearity, but it generates I. Okay, so how is that possible? That's only possible if this alpha equals 0. Okay. So alpha. So what we have here is I equals alpha times minus IS. Okay. Here I equals alpha times IS, and then here input is minus IS. Therefore I must equal alpha times minus IS. Okay. And alpha IS equals alpha minus IS, and that's only possible, and that's true for all IS's. That's only possible if alpha equals 0. And if alpha equals 0, regardless of IS, this current must always be 0. Okay, and that's an implication of symmetry. Now, alpha IS equals minus alpha IS. Therefore alpha equals 0, therefore I equals 0. Okay. And now let's figure out what it means that this current equals 0. Okay, what kind of benefits that we can get from that situation. Now, since I equals 0, under all circumstances, we can replace the bridge resistor R3 with open circuit, okay, by substitution theorem. The current through it is always 0, therefore we can replace with open circuit. But the current times the resistance is the voltage. Therefore, voltage is also always 0. And again, by substitution, we can also replace it by short circuit. And that should change the answer. Okay. Also, the voltage across R3 equals V equals R3 times I equals 0. Hence, we can replace R3 with short circuit. Okay. And either it's open circuit or short circuit. It's quite straightforward in that case to figure out input resistance seen from the port terminals. Okay. So this was the original one port, R1, R1, R2, R2, and this is R3. And now we have just discovered that no matter what you connect to the port terminals, there will be no current through R3. Okay, therefore, this resistor will always act like an open circuit. Or, since there is no current, resistance times current is the voltage. The voltage drop is also always 0. Therefore, this resistor also acts as if it's short circuit. Okay, so this is equivalent to either of the following cases, or both of the following cases. Okay, R1, R1, R2, R2, where R3 is replaced by open circuit, or replaced by short circuit. R1, R1, R2, R2. And both are easy to deal with. So we have 2R1 and we have 2R2, and they're in parallel. So we have 2 times R1 parallel R2 is the answer. Okay. Well, here we have R1, R2 parallel, and that is series to R1, R2, another R1, R2 parallel. So it's either 2R1 parallel with 2R2 or R1 parallel with R2 times 2, which both are the same thing. Okay? So this is equivalent to the following input resistance: 2R1 parallel R2. Okay. Now let's see another type of symmetry, and again try to figure out the input resistance. Example. Again, we have the same topology, but this time symmetry is along the vertical axis. Okay, we have R1, R1, and R2, R2. And for this, let's try to figure out input resistance by using symmetry. Okay. Now, for this, suppose that we want to apply the method of connecting a test source to figure out the input resistance. Okay, let's choose the test source of 1 amp. Okay, so from this, what we do is, to this, we connect one amp test source, R1, R1, R2, R2, R3. And suppose that, again, we're interested in whether there's any current flowing over R3 only. If there isn't, then we can just take it out and replace it by an open circuit, or just replace it with a short circuit. In either case, it's easy to figure out the input resistance. Okay. Now, because of symmetry, this current must be 0. It may not be obvious, but it becomes obvious once you consider, instead of this 1 amp, you consider, you connect two 1/2 amps current sources, okay, in parallel, which we can do, okay, because as far as this part of the circuit is concerned, they're exactly the same thing. What I mean by that is the following. This 1 amp, I now collect from 1/2 amp from here and 1/2 amp from here, just so that it looks exactly symmetric to the eye. Okay, so 1/2 amp here, 1/2 amp here. So by KCL, it's 1 amp entry, total of 1 amp entry, this circuit from this node. Okay. So this is R1, R1. This is R3. This is the current that we're interested in, and these are bottom resistors. Okay. Because of the symmetry, it's clear that whatever this current is, this current here must also be the same. Okay. So let's call those currents I1, and here we have another I1. Okay. It's the same current flowing over R1s. And then, because those two currents are the same and these two resistors or resistances are the same, it follows from KVL that this current must be 0. Why is that? Because, okay, let me, okay, so this, let me write KVL. Okay. KVL in this loop implies that we have R1, I1 plus R3 times I, and then plus this voltage, okay, plus minus, which is minus R1, I1, okay, must equal 0. So we have written KVL in this inner mesh, R1, R1, R3 mesh. So this and that, they cancel no matter what I1 is, and what we are left with is R3 times I equals 0. Okay, from which we see that I equals 0. And again, if I equals 0, you can replace R3 either by open circuit or short circuit, and the answer then is easy to reach. It equals R1 plus R2 over 2. Okay. We have R1, R2 in series and R1, R2 in series, and they're in parallel. Therefore, the overall resistance is the half of it. Okay. Now let's see another example. have the following circuit where all resistors are with resistances 1 ohm. Okay. Okay, everything is 1 ohm. And for this one port, the voltage source is connected, plus minus, and it's 26 volts. Okay, and we are asked for this current. Okay, current flowing over this resistor here. What's the current? Okay, now the axis of symmetry is this, the horizontal, okay? And if you call these currents I2 and I3, because of symmetry, it's more or less obvious that those two currents must be zero, okay? Why is that? Because consider, for instance, this case where we have 26 volts, and then what you do is you rotate the circuit around the axis of symmetry. Now, all the directions of these currents stay the same because we're doing rotation along that axis. Those currents are along that axis. Okay, so those currents stay the same, but the polarity of the voltage source changes. Okay, so this is 26 volts. It becomes minus 26 volts. Okay, so you apply 26 volts, you obtain I2 and I3. You apply minus 26 volts. You again obtain I2 and I3. That's only possible if I2 equals minus I2 or I3 equals minus I3, which means that those currents are zero. Okay? So by symmetry, we have I2 and I3 equals zero. Once a current through a resistor is zero, we can replace that resistor either by open circuit or short circuit. Okay? So let's replace it with an open circuit. Okay, if you do that, this circuit becomes equivalent to 26 volts. Everything is 1. And in this circuit, we're interested in this current I. Okay. Now this is equivalent to the following. We have plus minus 26 volts. Now, this resistance is, we have 1, 1, 1, 1, okay, they're all in series, so this makes 4 ohms, and that 4 ohm is parallel to 1, 1, 2 ohms, okay, and that 2 parallel 4 is in series with 1, 1, 2 ohms, okay, so this whole thing here is 2 in series with 2 in parallel with 4, okay? Which is 10 over 3 ohms. And then what remains is these two guys, 1, 1, it makes 2 ohms, and this is the current I. And here we have 1, 1, they're in series, that makes another 2 ohms. Okay? Now this circuit is considerably simpler to solve. solve then the original circuit, and the answer can easily be obtained as I equals 5 amps. Okay. Again, we have made use of symmetry, and that saved a lot of time. Okay. If you just ignore symmetry and try to solve the circuit, let's say, for instance, using node analysis, you would have to write many equations, okay, before you reach the answer. Now, in our last example, is somewhere in between example and exercise. Let's, along with symmetry, use also superposition or linearity. Okay. It's a very nice exercise which combines many different subjects into one problem. Okay. All resistors are again unity resistance. Okay. Yeah, 1 ohm resistor. Find the current I in the following circuit, and the circuit is as follows. So we have the following two-port. All the resistors are 1 ohm resistors, and from the port terminals we apply the following inputs. Okay. 10 amps from here, 6 amps from there. Okay. Now, even though the resistor part of the two-port and the fact that both we have the current sources on either side makes the circuit symmetric, there is one thing that harms the symmetry, and that is the fact that the magnitude of this guy and the magnitude of that input, they are not the same. Therefore, that breaks the symmetry. Okay? But still we have hope, thanks to linearity, and we can go as follows. We can follow the following hint. Okay. The input vector, okay, note that this is an input, this is another input, and we combine those two individual inputs to make the input vector to the circuit or to the two-port. Now, suppose that this is our first input vector, and this is our first input entry, and this is our second input entry. Okay, first, second, and that's our input vector. Okay, the input vector can be decomposed into the following sum. 10, 6 equals plus 2 minus 2. Okay, the sum of those two vectors, and what's important about those two vectors is that the magnitudes of both entries are the same. Here we have 8, 8, and here we have the magnitude 2 and 2. Here, of course, the sign is opposite. Okay, now what we can do is, okay, by the way, this is the current that we're asked. Okay. What we can do is, we can first consider this input, okay, 8 from here, 8 from there, and then in that case, the circuit would have some sort of symmetry, and using that symmetry, perhaps we can compute the component of the current, which we can call I1. And then we apply this input, that is 2 amps from here and 2 amps from over there. And then in that case, maybe we have a different type of symmetry, and that symmetry allows us to easily, perhaps, compute the component that we can call I2. And since the circuit is linear, we can combine those two components, I1 corresponding to this input, I2 corresponding to that input, and I1 plus I2 must give us the answer. Okay, so let's therefore, in step 1, apply this input and see what kind of symmetry that we can exploit. Step 1. Find the component I1 corresponding to this input in the following circuit. Eight amps, and now we're trying to figure out this current I1. Note that with this particular input vector, the circuit now is completely symmetric, okay, with respect to the vertical axis. Okay, now that's I1. Now to use symmetry, let's make a little modification on how we draw the circuit, but still it's the same circuit, therefore we can use this equivalent sign. Now what we will do is, to see the symmetry much better, we draw it in the following way. And then now, when you draw it like that, you have to be careful about the resistances. Okay. So what we modified is this thing and this, the in-between resistor. Okay. Now this was 1 ohm. Therefore, that 1 ohm can be written as 1/2 ohms and 1/2 ohm in series. Okay, this 1/2 plus 1/2, because they're in series, it gives us, okay, 1 ohm. As for this resistor here, it's 1 ohm, and that 1 ohm resistor can be written as 2 ohm resistors in parallel. Okay, this is 2 ohm and this is also 2 ohm. And we don't touch any other resistor, therefore all the remaining resistances are 1 ohm. Okay? And in this case, we're trying to figure out this I1. Now, consider the current that may be flowing over here. Okay, let's call this current, let's say, I3. Okay? Now, here we have I3. And then what you do is you rotate the circuit around the vertical axis, and what happens is this 8 amp becomes here and this 8 amp comes here. So still it's the same input that we apply to the circuit, but the direction of the current is changed. Okay, so you apply an input 8, you obtain I3. But for the same input, you also obtain minus I3, okay? That means I3 and minus I3 must be the same. And that's only possible if that current I3 is 0. So, in other words, we have no current over that wire, okay? So that wire is open circuit. Likewise, we have no current flowing over that wire. Likewise, we cannot have any current flowing over that wire. So no current on the alphas. Okay. Since there is no current, we can replace those pieces of wires with open circuit, or we can take a pair of scissors and cut the circuit in half without affecting anything here. Okay, so I want still be the same if you cut those 3 wires, and if you do that, the circuit becomes much simpler. Okay, hence. This thing here is equivalent to, as far as I1 is concerned, this current is concerned, to the following ohm. 1 ohm, 2 ohm. 1 ohm, okay. And here this is I1. Okay. This is a considerably simpler circuit than the original one, and we can compute I1. Okay. So I1 is found using that simple circuit. Now how about I2, the component corresponding to this input, 2 minus 2. Let's also say a few words about that situation and we'll be done. This example. So that was step 1. In step 2, we figure out the component due to 2 minus 2 input vector. Find I2 in the following circuit. Everything is 1 ohm. Okay, and this 2. Now, to make use of symmetry, we will make a little trick. And that trick is we will write this 1 ohm as 2 1/2 ohms in series. Okay? Which we can do without affecting the current here. So what we have here is, instead of a single 1 ohm resistor, we have 2 1/2 ohm resistors connected in series. Okay? So here we have 1/2 ohm, and here we have another 1/2 ohm. All the remaining resistors, they remain 1 ohm. Okay. Now let's consider the voltage drop or voltage difference between those two nodes, which I'm calling V1, or voltage difference between these two nodes, which I'm calling V2. Now, the claim is that both V1 and V2 are zero. There's no voltage drop between, or there's no voltage difference between those two nodes. Why is that? Because here we have the input vector 2 minus 2, let's say. Okay. And then what we can do is we can rotate the circuit along the vertical axis, and this 2 amp pointing down becomes here, and this 2 amp pointing up goes to the other side. So what happens is the following. If you do that rotation, input vector becomes minus the original input vector. Okay, 2 minus 2 becomes minus 2, 2. But that rotation doesn't change the polarities of those two voltages, V1 and V2. So V1 and V2 remain the same even if you apply minus the original input vector. And that's only possible if those outputs are zero. Okay? So by symmetry, we see that V1 and V2 must be zero. Since they're zero, there's no voltage difference between those two nodes. Those two nodes, what we can do is, by substitute theorem, we can connect all those nodes with wire. We can short circuit them, and if you do that, you in a sense separate left and right halves of the circuit. And if you do that, the circuit becomes much simpler to deal with when you want to compute I2. Okay. Therefore, as far as I2 is concerned, this is equivalent to 2 amp. 1/2 amp, 1 amp, excluding ohm, 1 ohm, 1 ohm, and these are all short circuits. Okay. Then we compute I2 in that simpler circuit. And finally, once we have what? I1 and I2, in the third step, step 3, because the circuit is linear time invariant, we can superpose those two answers. And the original current that we were asked at the beginning must equal, therefore, I1 plus I2, thanks to